to the Jones seminar. This afternoon, at some point, we will have a talk by Jeff Frolik from the University of Vermont. He's an associate professor in the School of Engineering at UVM. He heads the Sensor Network and Wireless Work Group, a team of faculty and students from engineering and computer science. He's a graduate of the University of Michigan with a PhD in EE systems, the University of Southern California with an MS in EE, and the University of South Alabama with a BSEE. And he's going to talk to us today about a really interesting interdisciplinary problem on everything from snow to wireless networks. Please welcome Jeff.
Thank you. So how's the audio? We good? All right, great. Well, the title of my talk, it's kind of winged together very quickly, is In Situ Monitoring of Snowpacks and Other Harsh Environments. So the talk is kind of broken into two parts, and if we get to the second part, that would be great, but if we don't, that's also good. And the idea is that in both environments, we're going to use wireless sensor networks. So I'd like this to be an engaging talk for me and for you. So if you have any questions, please let me know, and we'll tackle them in situ. Okay? So the overview, again, is two different parts. One, looking at what we can do in terms of understanding snowpacks better using wireless sensor network technology. And then the second part, again, if we get to it, is harsh propagation environments. Okay, we're going to set up these nodes that communicate wirelessly, and some of the environments aren't so nice in terms of the communication channel. So there's some things I'd like to discuss on work that we've done. Okay, so first disclaimer, okay? I'm an electrical engineer. My background is in comm systems. My foray into the snow environment has just been in the last 3 years, so I'm pretty much a newbie. But the work that we've done, we've shown to some pretty big players in the area, and no one's told us to leave the room, so hopefully it won't start today. Okay, so here's a study that was done by the Scripps Institute, and kind of identifies what we would expect to see with climate change, is that the water content in snowpacks is decreasing since the 50s in 8 of the 9 areas that they looked at. So the snowpack is changing. Things aren't the way they used to be. So the question that's kind of motivating our work is, how can we better monitor what is going on and use that information to understand the snowpack and eventually help manage our resources better. Okay, so when I talk about snowpack resources, I guess the geocentric view is really coming from the West Coast, where California kind of survives on the snowpack in terms of its agriculture and other water needs. Here so much, you know, we get rain year round, and the snow is good for other things. Okay, so here's just some images that you can pull off the web, and kind of showing us what they are looking at snowpack in the Eastern Sierras over 2 years. Up in the upper left, that blue area is Lake Tahoe. Okay, so kind of give you some frame of reference. And so we have data from 2 different years, you know, obviously very large scale that this data is being shown over. And what the colors represent is how many inches of water is in the snowpack, okay? So there's this metric called snow water equivalence, and basically it's a height. If you took all the water there, all the snow, melted it down, how many inches of water or centimeters of water does that correspond to? Okay, so this data comes from where? Okay. Well, it comes from remote sensing, comes from stations that are located throughout the Sierra Nevadas, kind of large structures, and it comes from a lot of modeling. all right? So it doesn't really tell us what's happening in a particular basin, for example, right? What's going on with the snowpack there. So the small scale understanding that's provided by an image like that just isn't there. It's a very large scale model. Okay, so people who deal with water in California, they would look at stuff like this and they say, okay, based on this data, we expect the spring runoff to be such and such cubic feet per minute, all right? Now, well, how good are they at doing this prediction? Well, it turns out that their nominal, the standard deviation is being off about 20%, okay? So the problem there, and as I mentioned this earlier, I'm repeating myself, is that if you overestimate the spring runoff, expecting too much water to come in, then you've drawn down your dams, and you're not going to fill them up, so you're just dumping water out to the ocean. If you underestimate the spring runoff, too much water's coming down, you have to release water and you introduce flooding. So that's not good. So you really would like to have a good understanding of the spring runoff. So the plus or minus 20% is, okay, that's not so good, but the scarier statistic that came from a snow scientist colleague is that 25% of the time you're off by 50%. Okay, so even though they've been doing these measurements that I'll be talking about shortly for many years, they've been doing the modeling, the predictions are still pretty bad. So there's kind of a misunderstanding of or a poor understanding of what's happening with the snowpack. So I think I covered a couple of these. I'll be using the term SWE a lot. Again, this is the snow water of equivalence. Remote sensing, that means you're taking the data from a plane or a satellite. So you're taking it from far. In situ sensing, you're on the ground, you're trying to come up with some ground truth measurement. And resolution is both in time and in space. So how close in time are you taking samples, and how far apart are your samples taken? So if you're doing any type of modeling that has some spatial sense and temporal change, you would expect the more data points you get both in time and in space, the better things are. All right? So that's kind of our motivation, is how do we enable something like that? Okay, so our problem statement is how can this spatial and temporal resolution for determining SWE be improved? Okay? And how can we do this in a method that's non-invasive, non-destructive, and also allows us to deal in complex terrains? Okay, well, this isn't too complex. It's a slope with some trees, but maybe you're considering an avalanche chute. Okay, how can you get in there and get some data? And so let's look at what people have done thus far. Well, first of all, let's look at an example of complex terrains. So in the trees, things are changing. You're not in a nice open plain. Okay, so here are some the standard in situ methods for monitoring snow or determining snow water equivalency. They kind of fall into two categories. One is the snow survey, where you basically send grad students out to the field with tubes, okay, and they go out and they shove the tube in the snow and they take it out, they measure how high the column is, they weigh it, tells you how much water is there, and then they go off and do the next site, okay. They asked California, I think it's Department of Water and Power or something, actually hires a whole crew of people to do this in the winter, and there was a snow history conference or something like that where I spent my sabbatical, and the guys that gave a talk on this, they just loved their job. Getting paid to go backcountry skiing was just like the dream, and they had these huts set up, and so it's kind of like we'd like to put them out of business, but I don't think they want to be put out of business. Okay, so the problem with this is that, okay, labor intensive, it's destructive. If you're going out there with your snowshoes or skis, you're disturbing that area, you're jamming a tube down there, you can't do that measurement again. All right, so, and then next time you want data, well, you have to go out there and do it again. So you don't get a lot of data in terms of time, right? You can do things arbitrarily close in space, but it's just manpower at that point. So the second approach is, well, you weigh the snow, okay? You just let the snow pile up on a scale, you weigh it, that tells you how much water is there. Well, the problem with that is that between the ground and the snow boundary, you get something called snow bridging. So basically these gaps, and if your scale's under a gap, then you're not going to be weighing anything, or if this gap's over here and your scale's here, then the load's going to be on this. So you get this variability between the ground and snow interface layer. So how do you deal with this variability is that you do an averaging filter, basically. You create a very large scale so that all these variations kind of get, averaged out. And so this is, that's a normal sized person there. And you can see he's putting in this thing on this flat surface. Looks like 4 queen size water beds. These tubes are coming out. They're being connected to pressure sensors. And then you can measure, with arbitrary fine temporal resolution, what the weight of the snow is. Okay, but certainly, this is not something cheap to do. You're going to have to drive to this with your equipment to put it in, most likely, and you're not going to put a lot of these things in there. So I argue that this has poor temporal resolution out there a lot, and this has poor spatial resolution because you can't put a lot of them out there. Okay, so here's a slide from a colleague, and I didn't do the typing, so that's not my typo. But here's what's going on. Okay, the grad student, and this is actually it is a grad student actually. I know this person. Shove the tube down. They're over here. They're weighing it, and here's the plot. They're going out 30-meter transects north and east and west. So they're collecting data every 5 meters. So you're getting some pretty good spatial resolution. But look at this last part here. They've gone out twice, okay? So they only have data points from twice during the year, all right? So one at peak accumulation and one at snow melt. So how can you improve on that? And, well, maybe here's an even more invasive approach, okay? Here's a very complicated station, all right? Whole bunch of instrumentation, just fabulous site to go to, but you're not putting a lot of these out there. So the spatial resolution is going to be really bad. And digging a snow pit, well, it's fun to do once. It was actually really fun. Filling it in wasn't so good, but digging it was fun. That's obviously very invasive. Okay, so how can we do things lower cost, less invasive, less destructive, easier, cheaper, faster, all those desirable things? So our new approach, and it's not so new anymore, but our approach is to see if we can use a wireless sensor network to do this. And so the idea is that you put out a lot of these stations, okay? Each station has sensors associated with it. The stations are sufficiently close together. You want them close together because you want some good spatial resolution. And because they're supposed to close together, they can communicate to each other. And then you have them communicate to each other, and then one node or one station has maybe a satellite radio or a cell phone. I mean, there's cellular coverage everywhere now, or not everywhere, but a lot of places. So you can just use a cell phone to dump stuff off to mission control. The guys with short sleeve shirts work, and you get the data, and then you do what you want with it. Okay, so that's the concept. So what have we done to try to make this happen? Well, this started a couple years back with a senior design project that was done at UVM, a mixture of CS, electrical and mechanical engineers. And the challenge to them was we wanted to put out stations out there, and we want it to last the winter. We want you to be able to backpack it in, hence their thing there. I actually drove to the site and they hiked in. We wanted to collect data. So at that point in time, we're only looking at 2 things. We're looking at just temperature of the air and snow height. So we had this little pinging circuit that measured the height. And when we put it out there, it worked. We all said it was great. And we went back there later, and the way we had set up this initial deployment was we didn't have a backhaul. All right, so we just had to go out. The plan was to go back out there once or twice during the winter and just pull out the stuff and dump the data off. But we had things like wire breakage, just all kinds of really mechanical packaging issues. So while the pictures are nice, the thing didn't really work for us. So we've been looking at how to improve this. But first of all, let's talk about what this project requires. So the students came up with this idea of SnowMAN for Snow Monitoring and Analysis Network. You know, that's the great thing about being an engineer. You can do acronyms all day long. So what does it require? Some embedded computing, all right? Low power radio to set up this network. Low power because we don't really have to worry about transmitting too far, and also low energy needs. We want this thing to last a long time. What temperatures sensors are we looking at? Well, snow depth. We have some studies that have been done that snow depth and SWE, do correlate. I guess we know that the more snow you have. Okay, thank you. Can I carry this around? Yeah, see if I like to move. Okay, so the snow depth and SWE are correlated, but depending on the density of the snow, you can't necessarily predict SWE from the snow depth. So we've been looking at new sensor technologies, or maybe new approaches to try to figure out what SWE is. So I'll talk a little bit about that. It needs an energy source. You got to power this thing. You want it to last the winter, so maybe you need to do some energy harvesting. Typically solar we would be using. We need networking among the nodes, and we need algorithms to set up the networking and routing from one node to the other, and also algorithms to look at the data, maybe compress it in some way, do some statistical analysis on it, so we minimize the amount of data that needs to be shipped from one node to the other. Because every time you do a transmission, you're drawing down your very limited energy source. Okay, so the argument is that we need a wireless sensor network. Okay, so before I get into much detail on what we've done, here's just another nice, this is a nice example that was done at, by UC Berkeley, and the idea is to monitor what the microclimates are in redwood trees. So this is kind of pretty well-known work in the community, so I thought I'd show it. So you can see we have different trees here. Each one has a different structure, and historically they've sent people up and down these trees to monitor stuff. And here's an example of some of the things they've done. Here's another happy grad student. And you can see basically they have a data logger up there, pretty high up in the tree, and have this stuff going on, got that stuff going on, and for a typical tree, you might have a kilometer of wires up there. So I think by looking at that, you say, well, if we could get rid of those wires, then we can certainly instrument a tree pretty quick, right? And then once we're done looking at that tree, we can move that infrastructure to another tree. So this is a really nice case for looking at a wireless system. And I would argue our snow deployment case is also a really good one to consider wireless, because rodents get into everything, and if you have wires hanging out connecting your sensor nodes, looking at height, those cables will they'll go away. All right, so here's the data that's come from the Berkeley deployment, and in the left column we're looking at temperature as a function of time to the day, and each line corresponds to a different elevation in the redwood, and the right column is the humidity. Okay, so you can start, when you start looking at data this way, you can start seeing some interesting things happening, and not so much right now, but pretty soon you're going to see the humidity just really start shifting a lot throughout the canopy, and this corresponds to kind of midday things that are going on. So all this data was collected with wireless instrumentation, thrown up in the trees, and then data's collected, and they've had this deployment up there for quite a while because the system was low energy. The nodes themselves lasted a while. So are we back in? back? Yes. Nice. Yeah, stupid wireless. Yeah, all right. How appropriate, right? Nice. Case in point, energy is critical. All right, so what we want is a non-destructive way to determine the SWE and the snowpack. So there's been some remote sensing techniques that have been used, gamma detectors and microwave remote sensing to look at snowpacks. So our thoughts are, well, why not use those ideas but scale them down to looking at lower cost implementations. So if things are low in cost, you can put more of them out there. Not only low in cost, but low in energy requirements. So we can integrate them with a wireless sensor network type package, right? Okay, so the first question we looked at is, can microwave attenuation be utilized? Okay, and the body of work out there, basically says, yeah, snow will attenuate electromagnetic energy. Okay, and so why is that? Well, if those double triangle things are antennas, and I'm setting up a communication link between one antenna and the next, and over a fixed distance I have lost L1, right? And I start adding snow where the permittivity is complex, and since it's a complex permittivity, I have an attenuation coefficient alpha and a phase constant beta. I'm going to get additional attenuation. Okay, so leveraging that, the more snow you get, the more attenuation you get, because the attenuation coefficient is dB per meter, let's say, and so the signal's going to go down. Okay, so that sounds good. So what does our data show? Well, before I show the data, the idea here is that we want to leverage low power commercial off-the-shelf chipsets. Radio chips, okay? So we're talking chipsets that are used in your laptop for Wi-Fi, your home phone, your, whatever else, router, okay? So things that operate at 433 megahertz, 915 megahertz, 2.4 gigahertz, and 5 gigahertz range. So stuff we don't have to go get licensing. So basically, use what's out there. And in one example, we may put a wireless sensor node operating at 2.4 gigahertz, and its only job, or maybe you hook up like soil moisture sensors to it, okay? But part of its job is simply to communicate to the node that's above the snow, and then we can measure that signal change over time. And can we correlate that to SWE? So that's the initial question. All right, so here's some data. And my little test setup here, I don't know how well you can see it, but I have a ladder with a boom coming across it. On the boom is a patch antenna. On the ground's another patch antenna. And basically, I'm using a vector network analyzer, so basically a piece of instrumentation meant to characterize filters, to look at the transmission loss between point A and point B. Okay? And then as the snow accumulates or the SWE increases, I'm getting these curves. Okay, so this is what I wanted to see, all right? The problem is, the way I took this data was not like the snow was naturally piling up. I basically went out there and I shoveled the snow on. I took a manual measurement, a SWE, and I did my S21 measurement, and it was all kind of taken at the same day when the snow was kind of slushy, all right? So this is the key point that we're going to come back to shortly. And also, you can see the total amount of SWE isn't that much, okay? So it's 10 centimeters. This might have been 30% snow, so 30% water in the snowpack, so 30 centimeters of snow. So not a lot of snow total. But this was kind of early data, and you can see we're looking at the different ISM bands there. Okay, so then I said, okay, well this is great. This is really promising. So I had a long-term deployment set up, and every day I'd go out and I'd monitor the attenuation loss, and things were nice and constant. And then one day I went out there and it had dropped suddenly. And I was like, okay, what's going on? The snow height hasn't changed at all. And it was in a warm spell that we had. And as the data shows here, early in the day, okay, so this is 9 in the morning after a hard freeze, the attenuation is about 37 dB. You know, come midday, we're at 43 dB. So we basically drop, what is that, 6 dB in the course of a couple hours. And these are 3 consecutive days, okay? So I'm coming back the next day, and boom, we're back where we started again, all right? So what's happening? So I'm looking on the ground, seeing if there's snow melt anywhere. No. I cut into the pack, and there's like these pockets of moisture in there. So what we see from this is that, you know, the idea of using microwave to monitor SWE probably in itself is not going to work. But it does gives us some interesting results. We can see things happening inside, but we can see that things are happening inside the snowpack with actually not cutting into the snowpack. All right. And so it's the effect that the snow itself is melting internally, okay, because it's warm, but it's not getting all the way down to the bottom. So why might this be useful? Well, if you had a system set up like this, you could maybe let people know who need to know, hydrologists and whatnot, that, okay, looks like the snow's starting to release, you know, spring runoff should be coming soon. Maybe you know that already because it's been warm, but you know, the snow is actually doing something, all right? But I have like a $25,000 piece of equipment that's telling you that, right? Okay. All right, so then the second idea is, okay, let's look at the natural radiation coming from the ground, and you know, they've deployed systems that fly around things to do this, and it's like, well, can we scale this down? So there's a solid state crystal type detector that's being developed I think it's been funded a lot by Homeland Security and other initiatives. That we have a handheld unit of, and I said, well, can I use this to, you know, look at snow? And so the idea here is that as the radiation's released, the detector gets it every time it gets a gamma particle. There's a voltage that's created proportional to it, all right? And then the snow will capture some of these, okay? Some of them won't get through. So the more you have, the more things don't get through, and the weaker, the fewer counts you're gonna get, the fewer returns.
Question for you?
Yeah.
Which is more efficient at capture, water or snow or ice?
I'm sorry, what?
Which is more efficient at capture of those photons, water or ice?
That's a good question. I do not know. I don't know. I think water is pretty good based on the stuff we've seen, but I haven't looked at ice at all, so I don't know. I'm not an ice scientist either. Okay. All right, so, well, is this true? With this device that the companies we contacted say that they'll get it down to about $500 in a couple years. Can we do this? Can we, you know, ascertain what's going on? So basically what I'm looking at is a range of energy between 100 and 300 keV, and the top plot is when the SWE is 200 centimeters. So this is a snow pit that, you know, the picture I showed earlier, I was doing the measurement there. So you get a lot of stuff going on, and when the snow gets really deep, you don't get so much stuff. So this is good. This is kind of what we wanted to see. Okay. So here's this long-term setup I had. Was right outside my office where I spent my sabbatical. And basically I'm just looking at that black box right here is where the gamma detector is. And at this point it's not integrated with the sensor node. We're just kind of seeing if this will work. And yeah, so as the snow gets deeper and deeper, here I got up to 40 centimeters of SWE. You know, we get this nice decay with repeatable measurement, and I got this one outlier that I just don't know what to do with, okay? But it's there. So this thing draws about 1/4 of an amp, okay? Each measurement took me a half an hour. So you start running the numbers, and it's like, well, maybe this isn't such a good, you know, device to use, at least not in this curved packaging, okay? But, you know, we are getting kind of the things that we had hoped to see. So this is promising, I think. Okay, so more data. You know, the question was, okay, is it going to be critical how high I have this detector? All right, if I put it on the ground or up above, you know, am I going to have to calibrate this thing? Is kind of the thing, or can I just throw it out there? Well, because the radiation is coming from the ground as a whole, you know, the indication to me is that basically you have this plane front that's coming up, and if there's only air there, nothing's capturing this energy, and it's going to get to your detector. And so you can see, you know, I go from right on the ground to over a meter high, and essentially I'm getting the same data within to the repeatability of the data. So that's kind of neat. This isn't so good. Okay. I said, well, doesn't matter where you take the measurements, you know, is everywhere in the Eastern Sierra is basically going to give you the same number of counts in 30 minutes. And, you know, where I live, that was good. Q8, the headquarters, that was kind of there. There's a hot springs that's in that area, so I took some measurements there while taking a soak. So that was pretty good. And then I went out to this deserted ghost town where they had done a bunch of mining. And you can see that, you know, okay, it's not so consistent, all right? So, you know, there's going to have to be calibration, at least per site. And the other question is, okay, how variable is this throughout, you know, a year or whenever you're going to do your deployment? So maybe the strategy is that you put out the system before the snow falls, do your calibration, come back after the snow's melted out, and retest. Okay, so here's the worst part of it all. Okay, so I was great. We dug this 4-meter snow pit. That was really fun, and was collecting data. And I said, well, I'll just do it every meter or so. You know, that's got to be enough, or you know, maybe every half meter. So I got some data points, and you know, the number of counts per minute is decreasing the deeper the snow is. So that's really wonderful. And then the data just. Nothing changes, all right? So basically this last data point's in the noise of the system. And looking at the literature and afterwards, you know, it's kind of 40 centimeters of water is kind of when things drop off. You just don't get enough stuff through to count anymore. And you're just looking at the noise of the instrument. So this seems to be the shortcoming of the gamma approach, is that you're not going to be able to look at really deep snowpacks. And so the question is what to do after that. I don't know yet. So you know, we have some future work to do on the sensor side. You know, maybe new detectors. The CZT crystal device was $5,000, and maybe it'll be $500. I found a really cheap online detector for $200, and so we're building up, and we're going to be testing it this winter. Okay, so you say $200, it's not going to be as good. Well, the point is, it's not as good. We know it's not going to be as good, but we're going to make up for that by giving more and more samples. Okay, and the reason why we can give you more and more samples is because you're going to spend the same amount of money, but you're going to get 10 times the number of sites. All right, so as opposed to one site. Okay, measurement consistency to different snow types. You know, what happens when we get a nice ice lens? Maybe to answer your question, you know, what happens in ice? You know, we'll need to look at that. Packaging, still an issue. Most of our problems, certainly at the beginning, were mechanical. You know, so it's a whole systems integration. Making sure that everything we do is low energy, the voltages are in the right range. We do proper signal conditioning so that it does interface with the wireless sensor hardware that we're buying, and running algorithms to not only do the networking and data aggregation, but maybe do some triggered sensing. Okay, we have temperature, okay, and ultrasound, and those are pretty low energy. We can do those all the time, and we wouldn't turn on this higher energy consuming, higher power consuming devices unless we saw some significant change. And so maybe the algorithm's running autonomously on the node, and it decides when to take the data, and also trades that off with how much energy it has available to take data. Okay, so my colleague in computer science is out in the Sierras this year at a different location, and he's putting in this installation. So this looks a little bit different than what the students drug out to the field, a little bit more ruggedized. Our battery source is just sitting here on the ground, so it's under the snow, so it's at a more thermally constant temperature. This is a reserve area, So we figured, oh, okay, this is going to be pretty good. But I got an email yesterday saying that he went out there to take a look at it. There were cows walking around it and were chewing on things. So, so much for that. But the thing was still working, so he was psyched. The blue box up there is where our radio hardware lives. The white thing kind of sticking underneath it is the sonar sensor. We're monitoring temperature. We're not doing any of the SWE stuff right now. So he's in computer science, so he's out there looking at the algorithms, kind of adaptive sampling, adaptive routing type issues. And here's a platform he can use to play with. And he likes to backcountry ski, so that's kind of his choice there. I think we kind of got all that covered. So this is what he's doing. I guess some things that are kind of interesting is that in addition to relying on the wireless stuff, in case things don't work out so well, we're also writing to an SD card in each of the nodes. So that gives us a nice backup. And this site that he's at is a research site, so there's a whole bunch of nice, research-related infrastructure, high data rate lines, and so he's leveraging that. There's also a whole bunch of larger snow stations that, for his particular deployment, is serving as a hub. And I think, here's the picture I have of it. And so, kind of a beautiful area. There's one of our stations there, and you can see that each one's pretty compact. You can carry out there. And this one, Google Maps is great, but not always. The green circles are the sites. The red triangle is the hub, and the extent of this is about 200 meters this way. So not a large area, but right now there's only one master site there, so we're adding some additional things to that. And you can see here we're kind of in the trees. They're in the trees, between trees. So the scientist that's working with us, that's kind of her motivation, is to see how these tree effects impact this. So since we're not sending a person out there, and we're not, to take the measurement, and we're not requiring this huge pillow, another thing we're thinking about is that, well, we now have this kind of infrastructure that we can put out there, and now we can do maybe other things. We can put this in an avalanche path, all right? Someplace you really don't want to send a person throughout the year, and we can do measurements there. So that's another type of complex terrain we're thinking about. Okay, so to wrap up the part about the snow work that we're looking at, so we're trying to apply some wireless sensor network technology to study snowpacks. In terms of sensors, we're scaling down approaches that have been used for remote sensing. And the power of the system, or the benefit we see it, is that it gives you better resolution both in space and time over existing in situ methods. So I'm going to switch topics here. So if there's any questions on the previous stuff, might be a good time. Okay. Well, people are moving, so that's not sleeping. Okay. All right. So, so as I mentioned, my background's electrical engineering. My bread and butter is comm, typically primarily at the physical layer. And so we had a contract to look at what the channel would be if you put wireless sensors aboard aircraft. So this is a MD-80, I think, that we're looking at. And again, we're treating this channel between two nodes as essentially a filter. And this data down here, we're sweeping the response across the band that we want to operate over. Okay, so this is the entire ISM band from 2.4 to 2.48 gigahertz. And you can see, hopefully you can see, well, you can see there's a lot of variation, okay? But what is the scale of that variation? Well, this is 10 dB. Okay, so in this particular trace across the band, we're getting about 20, 25, 30 dB variation. So this is far from a flat channel. Okay. Okay. Well, mobile communication systems have been studying fading channels, and there's models for that. there's Rayleigh fading and Ricean fading, and so we said, okay, well, maybe the best thing we could tell our customer is, what type of fading that they're going to be operating in, and then they can design mitigation techniques appropriately. So we started looking at the statistics, and then I thought we had an error in our code, okay, that analyzed the stuff, because what we found was that the channel fading was worse than predicted by the existing worst case model. All right, so what happened here? Well, let's look at the models for multipath. Okay, so then again, what we're looking at is what's happening in the channel between the transmitter and receiver. So the ideal scenario would be, let's say you're in outer space and you have two spacecraft communicating to each other. Basically, there's nothing reflecting anything, and you just have this line of sight component. So this LOS would correspond to these green arrows, okay, if you just look at the top. Well, since we're not in outer space and then we're at least, in a building or outside, it's going to reflect off other things. So we get these, pretty weak multipath components, and those are illustrated by the blue arrows in the top there. So that corresponds to a Ricean model, right? Now, Rayleigh fading is, again, the worst case considered for mobile communications. You just assume you don't have a direct line of sight. Everything's coming from the multipath. And you get this nice distribution, and it's great. It's really easy to work with. And then we get to what we found. And it's like things are worse than Rayleigh. Well, how can they be worse than if you don't have a primary path? It's all random. Well, we started looking at it and adapting some large-scale stuff to look at the small-scale problem. We said, well, what happens if you have two signals? And this considered just a direct line of path and another path rise at equal magnitude, but different phase. And you can think about if the phase is 180 degrees out, they're going to completely cancel. So the way this modeling works is that you assume a uniform phase, et cetera, and we wind up with, well, not this slide, the next slide, but we wind up with a condition that we're calling hyper-Rayleigh. Okay, so it's worse than Rayleigh. And the conditions are, you have very weak scatters, a few strong components, and this is stuff that we've actually measured in cavity environments. So it's like, okay, well, is this, how much have you measured? Well, we took, our collaborators took a lot of data on a rotor wing aircraft. Okay, I can't say the H word, but so they took this data and said, okay, let's look at it and characterize it in terms of the fading profiles. And you can see that this hyper-Rayleigh condition showed up about 20% of the time. And so our argument is that maybe this is something we shouldn't ignore. Okay, maybe this is the worst case condition we need to design for. Okay, so we came up with some models. And we said, well, we can't go out on a helicopter all the time. How can we emulate this? So we basically created the anti-anechoic chamber, okay, or it's a small-scale reverberation chamber. And the idea is that we can change the environment inside this chamber by mechanical means through rotating that blade there, okay, or we set up a phased array inside of it and we switch the elements of the array. So we can change the fading conditions quickly and repeatedly. So if you're testing certain algorithms or mitigation schemes with your radios, you can repeat these really harsh environments. And we can create a lot of these environments. I think my collaborators at South Florida have a 8-element array, and if you do all the permutations, it's like 1.x million permutations. So it's nice to have a high significant or high exponent in your number, I guess. So yeah, so this is what we've done in terms of the emulation, and here's some example data that we get out of this. So I mentioned the Ricean. Okay, so it's kind of a benign channel. You don't see a lot of variation. That's the green curve, and here's does anyone do mobile communications or fading channels? No? Okay, so I'm sorry. You asked me to talk about what I get excited about, and so now I am. So one thing we use in looking at fading channels is a cumulative distribution function. And so how you use this is you're trying to figure out the probability that the signal is going to be below a certain value and kind of eat into the margin of your system. So if you're designing a communication link, maybe you want a 10 dB margin, let's say. Okay, so what these curves tell you is that, well, if you have a 10 dB margin, how often are you going to blow it, okay? So if I look at the 10 dB on the axis, the negative 10 dB, so that's a fade, and I go up and I look at the Rayleigh curve, then you can say, well, about 5% of the time, I'm not going to make it, all right? So my communication link, you could say it has 95% availability. And if it's a rising thing, you say, well, 10 dB is good all the time because I never cross that. But look what happens if you go to, if your environment's actually this red one, and this occurs a lot in your system. If you design for a 10 dB fade, then you're going to not have this 95% availability. Not that 95% is good, but it's, potentially could be a lot worse. So the argument that we've been trying to make is that, if you're designing for sensors in a cavity environment, you need to really think about, how severe this channel can be and put in steps to mitigate them. And there's different mitigation schemes that have been used for mobile communications. The simplest, you look at the routers around here. How many antennas do you see on them? 2, okay? And why is that? Because if one's down, you just switch to the other one. And they're sufficiently far enough apart that the fading at one place is statistically independent from the other. All right? So if you just use a very simple concept of between just looking at what the strongest signal is versus the other, that's pretty simple. Even this dumb microcontroller sensor node can implement that. And I just saw some new chipset that is implementing it, so I'm really psyched that that's happening. Not because of me, because I think it's really good. All right, so the last thing that we're working on is trying to resolve the problem of, what I'm really interested in is not necessarily on the surface of a structure. I'm trying to figure out if this levee is going to blow, all right? So I'm trying to see if there's any weird things going on inside. So I'd like to encase something inside of it, or I'm looking at a concrete structure, and maybe I'm trying to see if there's any salt, if the concrete's starting to, there's any leaching involved. So I'd really like to embed a sensor deep into the structure. And I want it there for the life of the structure. So this thing could last 40 years, hopefully, maybe more. All right, and so you're not putting any type of battery in there. So you say, okay, well, I want some sort of passive device that does sensing, and then I want to be able to communicate with it. So there's technology called RFIDs. Everyone hear of that? Okay, so RFIDs are around. The problem with those is that they have a very limited range, because what you have to actually do is power up that with the electromagnetic signal to power like microcontrollers and things like that. So you got to really give it some power, all right? So you're talking really close scanning things and things you can't embed deep and stuff. So what we're looking at is based on a technology called a reflect antenna, okay? And essentially what it is a frequency doubler. And the way it doubles the frequency is kind of like running the signal through a diode. So it kind of rectifies it and you get these, you doubles the frequency at the out. And since there's no microcontroller, there's really nothing that requires voltage so much other than a diode bias. You can power it with a much lower signal, okay? Which means you can embed it deep into a structure. It doesn't require a battery. And then you say, well, okay, how do we do the sensing? Well, since the signal is essentially sending twice the frequency back than as to what you're interrogating it, the way you would interrogate it is sweep across the frequency band and look for the maximum return. And that's where the structure is resonant. And you can change the resonant frequency of the structure by a sensor attached to it. So as the phenomena changes, the sensor changes, it changes the resonant frequency of the structure, and the peak frequency you'll get back when you sweep across the band is going to shift. So it's kind of like looking at a filter shape that shifts over here when the temperature is hot and shifts over here when it's cold. So again, the idea is that this can be embedded deep into a structure. And so this is work that we're just starting. So it's pretty fun. There's something else about, so the other kind of nice, the vision for this is not that I'm going to walk around with a wand and scan the levee, but on the surface of the levee, I have a wireless sensor network deployed. Okay, so this is monitoring stuff on the surface, and I have its network going. Well, this network's operating at 2.4 gigahertz. I already have a 2.4 gigahertz radio on, so why not redirect that energy downward to scan my sensors embedded, okay, and then come back, relay the data I get back. So since this thing can activate at very low energy, I can use a very low power source, okay, something that's transmitting at very low power to interrogate it. So if you think about wireless sensor networks that I talked about earlier, we have these microcomputer boards with antennas, and they're hooked up to sensors, and they have this network. This would be like a layer below that. These are like really dumb, and they're designed to communicate with this infrastructure, okay? So even lower cost, lower energy, and you just get more of them out there. So increasing the resolution on all fronts. Okay, so obviously, as any faculty member knows, you don't do things alone. Okay, so a lot of great grad students, collaborators in CS and geography, funding through NASA Space Grant and NSF for this work, collaborations with UNR and UCSB. They've been really great in working with us on the SNOW project. UCSB and UNR, I mean, they have SNOW people. Those are the SNOW scientists, and they've been really patient with us as we get out there and play around. And then my collaborators at South Florida. Okay, so that's all I have. Yeah.
One quick question. How did you get that? Is that Photoshop?
No, my grad student said it to me. There's a reference in this corner here. I can't read it. It's really small. Yeah, it's something. Yeah. Grad students have time for that. Yeah. Why his thesis took an extra semester. Yeah. That's it. Yeah.
You didn't really mention the type of wireless network you were using for your snow investigation stuff.
Yeah, okay, so the stuff runs 802.15.4 Zigbee. They're motes. So that's a research platform, and it's really not good for this, I don't think, in the long run. So as mentioned in the meeting earlier, there's a new chipset that was brought to my attention that is incorporating not only antenna diversity, which is great, but also has, in addition to be able to transmit at 1 milliwatt, you can operate in a high power mode at 100 milliwatts to extend the range. So you can use the same chipset for like a hub and relate back to something further away. And maybe you give that particular node a bigger battery. So. Yeah, it still is. It's Zigbee. It's 802.15.4. I don't know if they have all the Zigbee stack, but the first couple layers are 15.4. Yeah. Yeah.
In your frequency interrogation, you're doubling frequency interrogation method. What kind of range can you interrogate from?
Yeah,
there, I guess that might vary with me.
Yeah, so then in the air, you're essentially looking at, well, it's part of the thing that we're looking at is, let's say you are going to interrogate for 10 feet above the ground, and then you have this strong boundary, basically the ground, and then coming back. So you are getting like returns from multiple places. So it is a multipath channel. So it's bringing the whole channel requirement aspect. But as compared to RFIDs, the good thing about, or what we think is promising with this design, is that the forward and reverse link are symmetric. In RFID, you really have a lot of power that you can pump into it, but what you get back isn't so hot, so that you're kind of limited on the return. But this is kind of symmetric, and the link margins look to be about between 20 and 30 dB more. So depending on the attenuation of the material, you can go an extra 20 dB deep. Now, what does that mean? Is that 6 inches or 6 feet? I don't know. It depends on the material. Yeah.
You do the snowpack monitoring in the eastern United States?
In my backyard, yeah. Well, the first deployment I showed you was at Mount Mansfield. It's right next to Stowe. I think what we're doing now at Sagehen, outside of Truckee, is I think that's going to be a really good test of the system. The snow is pretty severe there, and so in terms of mechanical testing and whatnot. But no, we don't have anything we haven't had the funds to bring this to scale. Let's put that way.
What are the, like, in your stow at the dead of winter, what are average maximum snow depths?
I think we can, in the east, we can get by with 2 meters. Yeah, our Sage Hen deployment was designed for 3 meters. There's another deployment that was done by UC Merced using a more elaborate, well, not elaborate, but more expensive system, and they were designing to like 4 meters. But this was like Tioga Pass, Yosemite type height, so really deep snow, yeah, which is fun.
Okay, I think if there are additional questions, Jeff will stick around for a
Yep.
few minutes, but let's thank him again.
All right, thank you.